Hello everyone. This video is about optimizing trajectories for spacecraft using golden section search method, a case study of satellites path to the target planet in the solar system. Next, introduction to golden section search method. The golden section is a mathematical ratio that is approximately equal to 1.618. It is often denoted by the Greek letter phi and is also known as the golden ratio, golden mean, or Devon proportion. The golden section has been used in various fields such as art, architecture, design, and even in nature. It is believed to have an aesthetic appeal and can be seen in many famous works of art and architecture, such as the Parthenon in Athens and the Mona Lisa painting. It is also appears in natural phenomena, such as the spiral arrangement of leaves on a stem or the growth patterns of the certain shells. The golden section search has also been studied in mathematics, particularly in geometry and number theory. The mathematical approach of the golden section. The golden section can be mathematically derived using the concept of continued fraction. Starting with a line segment AB, the golden section divides the segment into two parts, such as that the ratio of longer part to the shorter part is the same as the ratio of the entire segment to the longer part. Mathematically, this can be represented as AB by BC is equal to VC by AC, where AB is the total length of the line segment, BC is the shorter path, and AC is the longer path. Solving for the above length of AC, we get AC is equal to AB plus 1 plus square root of 5 into all divided by 2. The value of the approximation approximately equal to 1.618, which is the golden ratio or phi. The reciprocal of the golden ratio is equal to 0.618, is also considered to be a significant proportion in design and aesthetics, and it's also known as the golden proportion. The golden ratio and its related proportions have many interesting mathematical properties and have been studied extensively in number theory, geometry, and all other mathematics. Here we take an example on the above model. Suppose we have a function f of x is equal to x square minus 6x plus 5, and we want to find the minimum value of the function over the interval 0 comma 5. So first let us take the interval a comma b, which contains the minimum value of the function, means 0 comma 5, as in the above question. Step 2. Choose the point C and D in the interval A and B, and such that interval C and D is smaller than the A and B. So we have to take the interval between the 0 and 5, between the 0 and 5, which has to be smaller than the this above interval. So compute the function values at this point. We can find the C value as C is equal to A plus 1 minus 5 into B minus C, and D we can find like A plus 5 into B minus A, where we all know that 5 is a golden ratio and approximately it is equal to 0.328. And then we compute the function values fc and fd, f of c and f of d. So we find the c value and d value and f of c and f of d. Compare the function values at c and d and choose the new interval a comma b that contains the minimum value of the function. Since f of d is smaller than f of c, we know that minimum value of the function is in interval a comma d. So as we know that f of d is smaller than f of c, here, like here, so the interval will be like a comma d. So the the minimum to this minimum. Therefore, that we can set p is equal to d and repeat the process. Step 4. Repeat the same as step 2 and step 2 until step 2 and step 3. Like we have to take this interval. Like we got that latest interval now, a comma d. We have to take that interval as interval for the question. Means the f of x or the cost function. So we have to repeat the process until we get the interval is small enough to give us a good approximation of the minimum value of the function. So after finding all these iterations, we will get the interval a comma b is small enough, that is b minus a less than eta. This eta is a small positive number. Here is the Python code for the this above model, a unimodal model. Like import math, we all know that First we have to take the libraries, and that we have to fix the libraries and give the input, and then we will give the input and write the code. So like that, I will show you the output also. This golden section can be used in various applications like structural engineering, product design, aerodynamics, acoustics, and control systems. Yeah, now I will show you the output of the code. Here, see that, see this code, and by seeing looking it, you can understand the code. First, we will give the import. We will import that. We will give the a and b and cost function like that, and we will give that the phi value and all of that. And after that, you will get the, as in the above algorithm, you will write the code. So like this. Now I will run the code. You can check that. Yeah, here you can check that the optimal solution is v is equal to 10, theta is equal to 0.5, and minimum cost is equal to 10. So thank you.